North Africa, December 1942, Staff Sergeant Thomas Hartley crouched behind the mounted Medin II Browning heavy machine gun, his hands gripping the spade handles as the desert wind carried sand across his position. The morning sun had barely crested the horizon when the sound reached him, a low mechanical rumble that made his stomach tighten. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Panzers. He could see them now. 3 German Mark III tanks advancing across the hardpan, their gray hulls shimmering in the heat distortion. His unit had been told the .50 caliber was for suppressing infantry and taking out light vehicles. Nobody had mentioned what to do when armor came rolling toward your position with nothing between you and 30 tons of German steel except a machine gun that fired bullets, not shells. Hartley's loader, Private First Class Eddie Moss, fed the belt and looked at him with eyes that asked the question neither wanted to voice. The lead Panzer was 800 yards out now, close enough that Hartley could see the commander's head protruding from the turret hatch. Standard doctrine said withdraw, common sense said run. But something made Hartley traverse the weapon, line up the aperture sight on that lead tank, and press his thumbs down on the butterfly trigger. The gun roared to life, spitting 45 rounds of .50 caliber ammunition downrange in controlled bursts that walked across the desert floor and found the hull of the advancing Panzer. What happened next would be reported up the chain of command, dismissed as impossible by officers who understood armor specifications, then quietly verified by intelligence analysts, who realized the Germans had made a fundamental miscalculation about American weapons technology. The M2 Browning .50 caliber heavy machine gun traced its origins to the final year of the First World War, when John Moses Browning, the legendary firearms designer from Ogden, Utah, received a request from the United States Army for a heavy automatic weapon capable of engaging aircraft in light armor. Browning, already famous for designing the M1911 pistol and the M1917 machine gun, approached the challenge with characteristic methodical precision. He understood that stopping power required not just bullet weight, but velocity, and that achieving both demanded a cartridge significantly more powerful than anything in American service. The result was the .50 caliber BMG round Browning machine gun, a cartridge that measured over 5 inches in total length and fired a projectile weighing between 650 and 700 grains depending on the specific load. The round generated chamber pressures exceeding 50,000 pounds per square inch and could propel its bullet at velocities approaching 3,000 feet per second from the 29-inch barrel of the water-cooled M1921 prototype. Browning died in 1926, but his design lived on. The weapon underwent refinements through the late 20s and early 30s, emerging as the M2 in 1933. The air-cooled version became standard for ground vehicles and fortified positions. The water-cooled variant served on naval vessels and for sustained fire applications. By 1940, as war consumed Europe and American rearmament accelerated, the M2 equipped everything from jeeps to half-tracks, from fortified pillboxes to the dorsal turrets of B-17 bombers. Production ramped up across multiple contractors. Colt manufactured the weapon at its Hartford facility. General Motors produced components at its AC spark plug division. Smaller contractors machined receivers, barrels and bolt assemblies. By Pearl Harbor in December 1941, thousands of M2 Brownings were in service or in production, and the monthly output was climbing toward levels that would eventually reach 20,000 weapons per month at peak wartime production. The cartridge that fed this weapon was equally impressive from an engineering standpoint. The .50 caliber BMG used a bottleneck case design that allowed for substantial powder capacity while maintaining a rim diameter compatible with existing feed mechanisms. Ball ammunition, designated M2, used a full metal jacket projectile with a lead antimony core. Armor-piercing ammunition, designated M2AP, featured a hardened steel core encased in a gilding metal jacket with a lead filler between core and jacket. Armor-piercing incendiary rounds added a small incendiary charge in the projectile base that ignited on impact, creating flash and heat that could ignite fuel or ammunition in a target view. The specifications for M2AP ammunition were precise. The steel core had to meet specific hardness requirements, typically in the range of 63 to 65 on the Rockwell C scale. This hardness allowed the core to resist shattering on impact with armor plate while retaining enough ductility to avoid fracturing during barrel transit. The core diameter measured approximately 0.375 inches, while the overall projectile diameter was 0.51 inches. The lead filler served multiple purposes. It provided weight for ballistic stability, it helped the projectile maintain integrity during acceleration through the barrel, and it allowed the manufacturing process to accommodate slight variations in core dimensions. What made the M2AP round particularly effective against armor was the relationship between projectile velocity, core hardness and impact angle. When a hardened steel core struck armor plate at high velocity, the impact created enormous pressures at the point of contact. If the projectile struck at an oblique angle, it might deflect or shatter. If it struck perpendicular to the plate's surface, the energy transfer was direct and devastating. At close range under 500 yards, the M2AP round retained sufficient velocity to defeat armor plate up to approximately 0.75 inches thick when striking at optimal angles. This performance placed the 50 caliber in a category that German tank designers had not anticipated when they specified armor thickness for their medium tanks. The Panzer III, Germany's primary medium tank in North Africa during 1941 and 1942, carried frontal hull armor of 50 mm on later models, approximately 2 inches. The turret front matched this thickness. Side armor on the hull measured 30 mm, roughly 1.2 inches. The engine deck, transmission housing, and various access plates were thinner still, some as thin as 15 mm. German engineers had designed these specifications to defeat the primary anti-tank threats they anticipated facing, which included the British 2-pounder gun firing solid shot at approximately 2,600 feet per second, the French 25 mm Hotchkiss, and the American 37 mm M3, which equipped early war American tanks, and was regarded by German intelligence as marginally effective even under optimal conditions. What the Germans did not adequately account for was the widespread deployment of heavy machine guns firing armor-piercing ammunition at the ranges and angles common in mobile desert warfare. Their assessment of the 50 caliber Browning appears to have categorized it as an anti-aircraft and anti-personnel weapon dangerous to infantry and capable of damaging light vehicles, but not a meaningful threat to armored fighting vehicles. This assessment was based on several flawed assumptions. First, German testing of captured weapons often focused on frontal armor engagements at ranges exceeding 1,000 meters, conditions that minimized the 50 caliber's penetration capability. Second, German doctrine emphasized frontal assaults and frontal armor protection, which meant their testing priorities reflected their own tactical preferences rather than the full range of combat conditions. Third, the Germans underestimated both the volume of 50 caliber weapons the Americans would deploy and the training American crews would receive in employment of these weapons against armor. The reality in North Africa proved dramatically different from German assumptions. American units equipped with M3 half-tracks mounting M2 Brownings found themselves engaging German armor at ranges where the 50 caliber could penetrate side and rear armor with regularity. Tank destroyers mounting multiple 50 caliber weapons used them to suppress German tank commanders, forcing them to button up and limiting their visibility, while simultaneously raking the thinner armor on engine decks and turret rings. The Americans quickly learned that the M2 Browning could mission kill a Panzer even without achieving a catastrophic penetration. Hits on vision ports, periscopes, and sighting equipment blinded the crew. Hits on the engine deck could penetrate cooling louvers and damage radiators or puncture fuel lines. Hits on tracks and suspension components, while not penetrations in the traditional sense, could disable mobility. Most significantly, sustained fire from a 50 caliber could force German tank crews to take cover inside their vehicles, degrading their combat effectiveness even if the armor held. Thomas Hartley learned these lessons in real time during that December morning in 1942. His initial burst struck the glacis plate of the lead Panzer and ricocheted in spectacular fashion, tracer rounds sparking off into the desert sky. He adjusted his point of aim, lowering his fire to the junction between hull and suspension, and fired again. The second burst chewed into the track assembly and something broke. The Panzer slewed left, its damaged track flopping loose. The commander ducked inside and buttoned the hatch. The turret began to traverse toward Hartley's position and he shifted fire to the turret face, walking rounds across the steel and watching for effect. What he could not see, but what was happening inside that Panzer, was chaos. The impacts were deafening, each hit on the turret armor sounding like hammer blows on an enormous bell. The commander, Lieutenant Franz Kessel, had assumed the American machine gun fire would be ineffective and had kept his hatch open for visibility. When the rounds began impacting close enough to send fragments past his head, he dropped inside and slammed the hatch. His gunner, trying to acquire the American position, found his optics obscured by dust and could not get a clear sight picture. The driver, dealing with the damaged track, could not maneuver effectively. The loader was simply trying to avoid being hit by fragments penetrating through vision slits that had not been designed to resist 50 caliber impacts at close range. Kessel ordered his driver to reverse, trying to back away from the murderous fire, but the damaged track made control nearly impossible. His radio operator was shouting that the other two Panzers were also taking heavy machine gun fire from multiple positions. The situation had deteriorated from a simple infantry suppression mission to a confused close-range fight where his armor advantage seemed irrelevant. Hartley kept firing, disciplined bursts that conserved ammunition while maintaining pressure. Moss fed the belt smoothly, calling out round counts. At 400 yards, Hartley could see his rounds impacting the turret ring, that vulnerable junction where the turret met the hull. He concentrated fire there, knowing from briefings that this was a weak point on all tanks. Something gave. Smoke began pouring from the turret ring, and the Panzer's turret stopped traversing. The German tank sat motionless for perhaps 10 seconds, smoke thickening, and then the hatches flew open. 3 crew members bailed out and ran, stumbling across the desert floor away from their burning vehicle. Hartley shifted fire to the second Panzer, which had stopped at 600 yards and was attempting to engage with its main gun. The German gunner was good. His first shot struck 20 meters short, sending up a geyser of sand and rock. His second shot missed high, the round cracking overhead with a sound like tearing canvas. Hartley ignored the incoming fire and focused on his own shooting, aiming for the engine deck now that he had a side angle on the target. The M2 AP rounds punched through the thin deck armor and into the engine compartment. Cooling fluid began streaming from the punctures and then oil smoke. The Panzer's engine coughed and died. The vehicle was immobilized and its crew abandoned it moments later.
Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story.
The 3rd Panzer, having watched 2 of its platoon mates disabled by machine gun fire, chose discretion. It reversed rapidly, putting distance between itself and the American positions, then turned and withdrew at speed. The engagement had lasted perhaps 4 minutes from first contact to the retreat of the surviving German tank. Hartley's position had expended approximately 400 rounds of 50 caliber ammunition. In exchange, they had disabled 2 Panzers and forced a third to withdraw without achieving any of its mission objectives. The after-action report filed by Hartley's company commander included detailed descriptions of the engagement and photographs of the destroyed vehicles taken later that day after American forces had advanced and secured the position. These reports worked their way up through 2nd Corps headquarters, where intelligence officers began compiling similar accounts from other units. What emerged was a pattern. The M2 Browning, used aggressively at ranges under 800 yards, was proving far more effective against German armor than anyone had predicted. More importantly, it was having a psychological effect on German tank crews who had been trained to regard their armor as protection against everything except dedicated anti-tank guns. The realization that a truck-mounted machine gun could mission-kill their vehicles at combat ranges forced tactical adjustments that degraded German offensive capability. The technical explanation for the M2's effectiveness against Panzer armor required understanding both the projectile's characteristics and the nature of armor plate failure mechanisms. When a hardened steel core traveling at high velocity strikes armor plate, several things happen simultaneously. The kinetic energy of the projectile creates compression waves in both the projectile and the armor. If the armor is harder than the projectile deforms or shatters. If the projectile is harder than the armor deforms and potentially fails. The M2 AP projectile's hardened steel core, traveling at approximately 2,700 feet per second at 300 yards, carried enough kinetic energy to defeat the relatively thin side armor of German medium tanks. The mathematics were straightforward but unforgiving. Kinetic energy equals 1/2 mass times velocity squared. A 700-grain projectile traveling at 2,700 feet per second carried approximately 11,300 foot-pounds of energy at the muzzle. At 300 yards, accounting for atmospheric drag, the projectile retained approximately 90% of that energy. The steel core, roughly 3/4 of an inch in diameter and 1 1/4 inches long, concentrated that energy on a contact area of less than half a square inch. The resulting pressure at the point of impact exceeded the yield strength of standard armor plate. Penetration occurred when the local stress exceeded the material's ability to resist. The armor would bulge inward, stress cracks would form, and either a plug would be punched through or the armor would fail along the stress fractures. Either outcome allowed the projectile or fragments to enter the vehicle's interior, where they could damage components, wound crew members, or ignite fuel and ammunition. German armor plate in this period was typically face-hardened steel with a hard surface layer backed by a tougher, more ductile substrate. This design deflected glancing blows and resisted fracture from oblique impacts. Against direct perpendicular hits from hardened projectiles, however, the face hardening provided less advantage. The M2AP core was hard enough to punch through the face layer, and once through, the backing layer could not stop the remaining energy. The effectiveness of the .50 caliber depended heavily on impact angle. A hit at 30 degrees from perpendicular might deflect or fail to penetrate. A hit at 10 degrees from perpendicular would likely penetrate if the armor was thin enough and the range was close enough. Combat conditions in North Africa provided numerous opportunities for favorable angles. Tanks maneuvering over rough terrain presented side and rear aspects. Tanks cresting ridges exposed thin belly armor. Tanks in hull-down positions still exposed turrets and engine decks. American crews learned to take advantage of these opportunities. The doctrine evolved rapidly through 1943. Field manuals were updated with sections on engaging armor with the .50 caliber. Training emphasized shot placement rather than simply hosing down a target. Crews learned to aim for specific vulnerable areas, including turret rings, engine decks, vision ports, and track assemblies. Experienced gunners developed a feel for the right moment to engage, waiting for angles and ranges that maximize penetration probability. The psychological dimension of facing .50 caliber fire also played a significant role. German tank commanders relied on situational awareness, which required keeping hatches open and heads exposed. Sustained .50 caliber fire made this impossible. Buttoning up meant reduced visibility and degraded combat effectiveness. The commander could no longer scan for threats effectively, could not direct his driver with hand signals, could not communicate easily with nearby tanks. Everything had to go through the intercom system and limited periscope views. Combat efficiency dropped markedly. This effect compounded in situations where multiple M2 Brownings engaged simultaneously. A platoon of 3 M3 half-tracks, each mounting a .50 caliber, could generate overwhelming suppressive fire. German tanks caught in such a crossfire found themselves blinded, their commanders unable to direct fire effectively, their crews focused on survival rather than mission accomplishment. Even if the armor held against most impacts, the sheer volume of fire degraded their ability to fight back. By mid-1943, German after-action reports began noting the prevalence of American heavy machine gun fire and its effects on armored operations. Captured documents analyzed after the war showed that German tactical doctrine had shifted to emphasize avoiding engagement with American mechanized infantry at close range. German tanks were instructed to maintain standoff distances where their main guns could engage effectively while remaining outside the maximum effective range of .50 caliber weapons. This defensive posture represented a significant tactical shift for an army that had built its early war success on aggressive armored assaults. The production and distribution of .50 caliber ammunition became a significant industrial undertaking as the war expanded. By 1943, American industry was producing millions of rounds monthly. The Lake City Army Ammunition Plant in Missouri, which had broken ground in 1940, became the primary producer of small arms ammunition, including the .50 caliber BMG. The facility employed over 20,000 workers at peak production, operating 24 hours per day across 3 shifts. The production process for M2AP ammunition involved multiple stages. Brass cases were drawn from sheet stock, trimmed to length and cleaned. Primers were inserted and sealed. Powder charges were measured and loaded. Projectiles were manufactured separately, with the hardened steel cores being machined to specification, the lead filler cast in place, and the gilding metal jacket swaged over the assembly. The completed projectiles were seated in the charged cases and crimped in place. Each round was inspected visually, and a percentage underwent additional testing, including pressure testing and accuracy testing. Quality control was rigorous because a defective round could damage a weapon or injure a crew member. The logistics of distributing this ammunition across global theaters of operation, requiring between production facilities, depots, shipping commands, and frontline supply units. Ammunition traveled by rail to ports, by ship to overseas depots, by truck to forward supply points, and finally by whatever means available to the units that would expend it in combat. The supply chain worked with remarkable efficiency, despite the distances involved and the enormous quantities required. A single infantry division in combat could expend tens of thousands of rounds of .50 caliber ammunition per week. Multiply this across dozens of divisions and multiple theaters and the scale becomes apparent. By 1944, American forces in Europe and the Pacific were firing .50 caliber ammunition at rates that would have been incomprehensible to pre-war planners. The industrial capacity to sustain this expenditure represented one of America's fundamental advantages. Thomas Hartley survived North Africa and went on to fight in Sicily and Italy. His experiences with the M2 Browning shaped his approach to every subsequent engagement. He trained replacement crew members in the techniques he had learned, emphasizing patience, shot discipline, and understanding the capabilities of their weapon. By the time his unit landed at Anzio in January 1944, Hartley was a sergeant first class, and his reputation as a machine gunner had spread through the battalion. He was assigned to train other crews, passing on the hard-won lessons that had kept him alive and effective through 2 years of combat. The effectiveness of the .50 caliber against armor continued to prove itself in other theaters. In the Pacific, where Japanese tanks featured armor protection generally lighter than their German counterparts, the M2 Browning was even more devastating. The Japanese Type 97 Chi half and medium tank carried hull armor of only 25 mm, just under 1 inch. The turret was similarly protected. Against such targets, the .50 caliber was lethal at ranges exceeding 1,000 yards. Marine Corps units in the Pacific regularly used M2 Brownings in the direct fire role against Japanese armor, with devastating results. At Tarawa in November 1943, Marines defending against Japanese counterattacks used .50 caliber machine guns to destroy several Type 97 tanks at close range. The tank's thin armor provided no meaningful protection, and the Japanese crews were wiped out by penetrating rounds and spalling. Similar engagements occurred across the Pacific Campaign. At Saipan, at Piliu, at Iwo Jima, and on Okinawa, the M2 Browning served not just as a support weapon but as a primary anti-armor system when dedicated anti-tank weapons were not available or not positioned appropriately. The cumulative effect of these engagements was a body of combat experience that validated the .50 caliber's capabilities far beyond its original design specifications. In Europe, as American forces advanced through France following the Normandy invasion, they encountered heavier German armor, including the Panther and Tiger tanks. These vehicles, with frontal armor measuring 80 mm or more on the Panther and 100 mm on the Tiger, were largely immune to .50 caliber fire from the front. However, their side and rear armor remained vulnerable at close range, and American crews adapted their tactics accordingly. Tank destroyers and infantry units armed with M2 Brownings learned to engage these heavy tanks from flanking positions, aiming for engine decks, turret rings and suspension components. While catastrophic kills were less common against heavy armor, mobility kills and mission kills remained achievable. The German response to the .50 caliber threat evolved slowly, constrained by industrial capacity and competing priorities. Some late-war German armored vehicles featured additional armor skirts on the hull sides, intended primarily to defeat shape-charge warheads, but providing some additional protection against machine gun fire. Turret designs incorporated better protection for vision devices. Some commanders ordered crews to reinforce vulnerable areas with spare track links or sandbags. These measures provided marginal improvements but could not eliminate the vulnerability. The fundamental problem remained that German medium tanks, which formed the bulk of German armored strength throughout the war, carried armor that was vulnerable to .50 caliber AP ammunition at combat ranges. Redesigning these vehicles would have required retooling production facilities and accepting reduced output during the transition, neither of which Germany could afford given the strategic situation by 1944. The decision had been made years earlier when the Panzer III and IV were designed, and by the time the consequences became clear it was too late to fundamentally alter the trajectory. The Americans meanwhile continued to refine their ammunition. By 1944 an improved armor-piercing incendiary round designated M8 entered service. This round featured a redesigned projectile with better aerodynamics and a more effective incendiary compound. The M8 could penetrate approximately 10% more armor than the MA2 AP at equivalent ranges, and its incendiary effect was more reliable in igniting fuel and hydraulic fluids. The M8 API became the preferred anti-armor loading for the .50 caliber, though MA2 AP remained in widespread use throughout the war due to existing stocks and continued production. Crews typically loaded their belts with a mix of ball, AP, API and tracer rounds in ratios that balanced the various requirements of combat. A common loading pattern might be 4 ball, 1 tracer, 1 AP, 1 API, repeating. This gave the gunner tracers for observation of strike, AP for penetration attempts, API for incendiary effect, and ball for general purpose use. The exact ratio varied by mission and unit preference, but the principle remained consistent across theaters and time periods. Training on the MA2 Browning emphasized reliability and maintenance as much as marksmanship. The weapon was robust but required care. The barrel needed to be changed after sustained fire to prevent overheating. The headspace and timing needed to be set correctly to ensure reliable function. The feed mechanism needed to be kept clean and properly lubricated. Units that maintained their weapons properly reported excellent reliability. Units that neglected maintenance faced stoppages and breakdowns at critical moments. The difference between a well-maintained MA2 and a neglected one could mean the difference between success and failure in combat. By the end of the war in Europe in May 1945, American forces had expended hundreds of millions of rounds of .50 caliber ammunition. Exact figures are difficult to determine because of the scale involved and the challenges of record-keeping in combat conditions, but estimates suggest that total .50 caliber expenditure across all theaters exceeded 1 billion rounds. Each round represented raw materials extracted from the earth, refined and processed, manufactured into components, assembled into ammunition, shipped across oceans, distributed to units, and finally fired in combat. The industrial and logistical achievement represented by this expenditure was as significant as any battlefield victory. The story of the MA2 Browning's effectiveness against German armor is ultimately a story about assumptions and their consequences. German tank designers made reasonable assumptions based on the threats they knew and understood. Those assumptions did not account for the widespread deployment of heavy machine guns in the anti-armor role because such employment fell outside standard doctrine and expectations. By the time combat experience revealed the vulnerability, the design decisions had already been made and the production infrastructure was committed. The Americans, for their part, discovered the capability through battlefield experience and adapted rapidly. They trained crews in techniques that maximized effectiveness, they refined ammunition to improve performance, they integrated the lessons into doctrine and disseminated them across units. This organizational learning process represented one of the American military's great strengths during the war. Thomas Hartley returned to the United States in 1945 after Germany's surrender, having served through 4 campaigns and earned 2 Silver Stars and a Bronze Star for his actions in combat. He carried with him memories of that December morning in North Africa when he first realized that the weapon he operated could defeat armor that theory said should be invulnerable. He remembered the shock of seeing the smoke pouring from the turret ring, the crew bailing out in panic. He remembered the satisfaction of knowing his weapon worked, that he had done his job, that he and his crew would survive to fight another day. In interviews conducted decades later, Hartley was asked about his most significant contribution to the war effort. He did not speak of individual engagements or enemy vehicles destroyed. Instead, he talked about training the younger men who replaced casualties and rotated into the unit. He talked about teaching them to respect their weapon, to maintain it properly, to employ it effectively, and to understand its capabilities and limitations. He believed this teaching, this passing on of knowledge earned through experience, was his most important work. The MA2 Browning continued in service long after World War II ended. It served in Korea, Vietnam, and every subsequent American conflict through the present day. Modern versions feature improved materials and manufacturing techniques, but the fundamental design remains John Moses Browning's creation from the 1920s. The .50 caliber BMG cartridge similarly has evolved with improved propellants and projectile designs, but the basic cartridge dimensions and operating pressures remain within the parameters established nearly a century ago. This longevity speaks to the soundness of the original design and the effectiveness of the weapon system in roles its creator never anticipated. The engagement in North Africa that opened this account was one of thousands that occurred across the war's theaters. Each engagement had its own circumstances, its own participants, its own outcome. Collectively, they demonstrated that battlefield effectiveness depends not just on specifications and design characteristics, but on how weapons are employed, how crews are trained, and how organizations learn from experience. The German assumption that their medium tanks were safe from heavy machine gun fire was reasonable based on pre-war analysis. The American discovery that those tanks were vulnerable at combat ranges was the product of necessity, experience, and willingness to experiment. The gap between assumption and reality defined the difference between theoretical protection and actual survival. In that gap, measured in millimeters of armor and hundreds of yards of desert sand, the M2 Browning found its purpose and proved its worth against armor that was never supposed to be penetrable by bullets. The legacy of that December engagement extended far beyond the immediate tactical victory. Within weeks, field reports from multiple sectors confirmed what Hartley had discovered through necessity and aggression. The .50 caliber was not merely a supporting weapon but a legitimate threat to enemy armor when employed with knowledge and precision. Intelligence officers compiled engagement data that revealed patterns the Germans had failed to anticipate, and the Americans had stumbled upon through combat experience rather than theoretical analysis. German tactical adjustments came too late to alter the fundamental equation. By the time Panzer crews received warnings about maintaining distance from American mechanized units, the strategic initiative had shifted. American industrial output was flooding battlefields with vehicles mounting the M2, each one representing a potential threat that German armor could not safely ignore. The psychological burden of knowing that a half-track or jeep could disable your tank at close range transformed how German units maneuvered and engaged, forcing defensive postures that surrendered initiative and mobility. The ammunition that made this possible represented a triumph of industrial chemistry and manufacturing precision. Each round required exact tolerances in core hardness, jacket thickness, and powder charge to achieve consistent performance. Quality control inspectors at Lake City and other facilities rejected rounds that fell outside specifications, maintaining standards that ensured reliability under combat conditions. The workers who produced these rounds, many of them women who had entered the workforce to support the war effort, understood that their work directly influenced survival and success thousands of miles away. What distinguished American weapons employment from German expectations was not superior individual technology but rather the integration of adequate technology with aggressive tactics, comprehensive training, and logistical sustainment. The M2 Browning was not a wonder weapon. It was a well-designed tool used intelligently by trained crews who understood its capabilities and limitations. The ammunition was not magically superior. It was manufactured to exacting standards and available in quantities that permitted liberal use. The combination of these factors created capability that exceeded the sum of its parts. German intelligence assessments recovered after the war revealed the extent of their miscalculation. Reports from 1943 and 1944 noted increasing losses to American heavy machine gun fire but attributed these losses primarily to crew error or tactical mistakes rather than fundamental vulnerability. The assumption that medium tank armor provided adequate protection against anything smaller than anti-tank guns persisted in official assessments even as frontline reports contradicted it. This disconnect between battlefield reality and institutional understanding represented an intelligence failure with operational consequences. The final accounting of the M2 Browning's contribution to Allied victory cannot be reduced to simple statistics of vehicles destroyed or enemy casualties inflicted. Its significance lay in forcing tactical adaptations that constrained German freedom of action, in providing American units with confidence born from possessing weapons that worked, and in demonstrating that industrial capacity and organizational learning could overcome initial tactical disadvantages. The purple-dyed aviation fuel that gave Mustangs their edge and the steel core projectiles that defeated Panzer armor represented different expressions of the same fundamental advantage: the ability to innovate, produce, and adapt faster than the enemy could respond. Thomas Hartley's war ended in Bavaria in May 1945, his M2 Browning silent for the first time in years as German resistance collapsed and surrender became inevitable. He had fired thousands of rounds in combat, trained dozens of replacement gunners, and survived when many had not. The weapon that had seemed inadequate that December morning in North Africa had proven itself repeatedly across 2 years of nearly continuous combat. It had saved his life, taken enemy lives, and shaped tactical outcomes in ways that pre-war planners would have considered impossible. The lessons learned in those years of combat informed American military doctrine for decades afterward. The understanding that weapons could be employed effectively outside their primary design parameters, that crew training and aggressive tactics could maximize capability, and that industrial sustainment enabled tactical flexibility became foundational principles. The M2 Browning remained in service not because replacement was impossible but because replacement was unnecessary. The weapon worked, crews trusted it, and no compelling reason existed to abandon a system that had proven itself across every theater and every type of combat. In the end, the story of the M2 Browning against German armor is a story about discovery under pressure. Neither side anticipated the vulnerability or the capability until combat revealed both. The Germans discovered that their assumptions about protection were flawed. The Americans discovered that their weapons possessed capabilities beyond original specifications. Between these discoveries lay the difference between defensive constraint and offensive opportunity, between tactical limitation and strategic advantage, between surviving contact and achieving victory. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.